Hello, welcome to the continuation of our lesson on moment distribution method of structural analysis. This is part 3 of the lesson, so in case you have not watched part 1 and 2, I'll advise you to watch so that you can follow what we are doing. My name is Engineer Dr. Gideon Giam from the Department of Civil Engineering at Akwa Ibom State University. So in this part 3, we're going to continue from where we stopped in part 2. And that will be to look at beam with simply supported end. What we have been looking at in previous examples have been cases where the support are fixed. But what happens when either or both of the support is simply supported? That is what we are going to look at. What you ought to have in mind is to remember that for member span simply supported at both the knee and the far support, the stiffness factor is what? K equals to 3 EI over L. So we are going to look at this example 3, which we are to analyze and draw the bending moment and shear force diagram of this beam. So let's take note of the beam. It has 3 spans, but take note that at this support A, which is the end support, the end left support, it is simply supported. That's where the difference is. So what we do is, as first thing is to calculate the stiffness factor. Stiffness factor for AB. Remember, it is simply supported here and continuous here. So we take it as 3 EI over L. So that gives us this. For span BC, continuous here, continuous. So it is 4 EI over L. That gives us this. For span BC, it is continuous here and fixed. So it is still 4 EI over L. So once we do that, we have been able to calculate our stiffness factor. The next thing is to calculate our distribution factor. Take note that this is support A. The distribution factor here will be 1. The distribution factor here will be 1. Where we need to calculate the distribution factor is at support B and at support C, where we calculate the distribution factor to be this and this. So we go to the fixed end moment. As usual, we calculate the fixed end moment. The main thing is the moment distribution. So this is the load, the beam. We put the distribution factor that we have calculated. We put the fixed end moment. Remember, the fixed end moment here is minus 14.4. This one is 21.6. This is because in span AB, the point load is not at mid-span. So if you go back to the lesson, part 1 of this lesson, where we mentioned the simple common cases and their fixed end moment, you notice that the fixed moment at this point is going to be P A B squared. This is P, this is A, this is B. You square the B all over L. So that's why we have this place is P A B squared all over L squared. That gives us minus this. While this one, where is the opposite one? Is P A squared B all over L squared. Go back to that table to look at it again. So once we put the fixed end moment here, the first thing we do, we want to maintain, this is a simple support A. So we want to keep the moment at 0. So we balance this moment minus 14.4 by introducing a moment of the same magnitude but opposite in direction. So that's why we introduce 14.4. So that when you do minus 14.4 plus 14.4, it will give you 0. It will give you 0. And so we now, once you do that, don't take over moment to that support again. We now come here and balance this one. To balance this one, remember it's 21.60 minus 24.38. And you now take the excess moment, which is going to be an anti-clockwise moment, introduce the same clockwise moment of the same magnitude, and distribute it to this joint based on their distribution factor. You do the same here, find the excess load, introduce a moment, and find the excess moment, and introduce a moment of the same magnitude but opposite in direction. Distribute it to this two member meeting at that joint based on their distribution factor. Once you do that, the next one, remember, notice that moment is carried over to this here, but moment is not carried over to this support because we don't want to change. We have maintained it as 0. So you carry over here, carry over this one to this place, carry over to this. You can see carry over to here because it's a fixed support. After that, we balance again. When you balance again, carry over, carry over, carry over. Notice at all the stages, no moment is carried over to this support because we have balanced it once and for all. So having done that, you now sum the load. When you sum it, you have here the sum, the support moment, and you can go ahead as usual to calculate the support reactions. The support reaction, as usual, we split the beam into simply supported beams. So this is span AB. Remember the support moment here was 27.67. No support moment here. So if you speak span AB and take moment at A, you will have this load 30 is going to produce a clockwise moment. That is why it is plus. So 30 times the perpendicular distance is 3 plus this 27 is actually the clockwise moment here, which is 27.67, while the moment due to VB1 is going to be an anti-clockwise moment. So VB1, because it is anti-clockwise, that is why it is minus. So VB1, 5 is the distance from the load to the where you are taking moment. So we equate the whole of them to 0. The only unknown here is VB1. If we solve for VB1, it gives us 23.53 kilonewton. So we come to point B and take moment again. Take moment at point B, you have this equation. The only unknown is VA. If you calculate for VA, it gives 6.47. So we go to span BC. Take moment at B. We have this equation. You calculate for VC1. Then take moment again at C. You have this equation and calculate for VB1. So we go to span BC and do the same. Calculate for VD and for VC2. So when we come here, our VA is well pronounced. VB will be VB1 plus VB2, which gives us this. VC will be VC1 plus VC2, which gives us this. And VD we have calculated. So the next thing is for us to go and draw the shear force and the bending moment diagram. The shear force diagram is drawn as usual, but just take note at this point because we have to load acting at this point. At here, this reaction 69.83 will push the shear force to 46.3. So between here and here, a distance of 1.5 meter, there's a UDL of magnitude 25, but distance is 1.5. So if you do 25 times 1.5, you have 37.5. So the UDL 37.5, because this UDL will move it horizontally to here. So this minus 37.5 gives you this 8.8. But there's a point load of 15 kilonewton. So the point load will press it vertically by 15 kilonewton. And that is where we have this 6.2. While the remaining UDL from here to here is also 35.5. So it's going to push you to here again when this 79 reaction of 79.61 will push it up, and this other UDL will push it to this place, then this reaction will push it to the neutral. So that's it. The next thing is the bending moment diagram. The bending moment diagram, I'll first of all draw the support moment diagram. There was no moment here, so it's 0, 27.67, 23.77, 24.12. So that's the support moment. You now take the simply supported moment for each of the span and superimpose. So for here, take note of this. Here, you're going to have at this So in the bending moment diagram here, it's a little tricky, but if you follow what I'm going to say, you get it. This load is not at mid-span. It's at a distance 3 meters from the left support, 2 meters from the right support. So the simple supported moment for this is not going to be PL over 4, but it's usually PAB over L, where in this case P is 30, A is 3, B is 2, L is this plus this, which is 5. So it's going to be 30 times 3 times 2 divide by 5. And if you do that, you're going to have 36. Take note of that. You have 36, the magnitude of the simple supported moment. Now, again, for us to know this point, which is directly where the maximum load is, it's all going to be this plus this divided by 2 because that mid-span that is not the middle. In this case, it's going to be, you have a load of 27.67 here, you have 0 here, and the thing is moving serially. So at this point, which is 3 meters from here, you're going to use a concept of similar triangle or the concept of interpolation to find the magnitude of moment at this point. So if you do that right, you're going to have 16.6. So this is 6.6. So for you to now have this point, it's going to be 36 that you calculated from PAB over L minus the moment here, which moment of 16.6. So that was how we had this 19.4. Try doing that on your own. You do it. So while these other ones are the same, where you have this moment here and this moment here, to know what is at the mid-span, it is this plus this divided by 2. You have something here, and this moment was originally WL squared over 8. So you now subtract this from WL squared over 8. That's what gives us what is here. The same thing is done here at this moment. But please take note that the load here is not just going to be WL squared over 8. It's going to be WL squared over 8 plus PL over 4. Remember, there are two moments here. Take note of that, I just remember. So PL over 4 plus WL squared over 8 is what you're going to have from here to here. Then you subtract this midpoint from there. It will give you this. This one is just going to be the usual one. So with that, we have been able to calculate to draw a bending moment and shear force diagram for a beam with simple support at the end. The next case is when we have a beam with cantilever end. So when a beam is overhanging at this one or both end support, the bending moment at the support near the overhanging end will be due to the load over the overhanging portion and will remain constant irrespective of the moment on the other support. And the distributing factor over the support having one span overhanging will thus be 1 and 0, as you will see when we go to the example. Moreover, what you should note is that for the sake of this support is taken as simply supported for the purpose of calculating stiffness factor. Take note of that. And so, example 4 here, we have a beam that have a cantilever at this left support A. Cantilever is 15 kilonewton and is acting over a distance of 1.5 meter. It is a very common thing we meet in real life structural analysis. So let's go to what we do. So for the loaded beam beside, which is this, a cantilever moment, an anti-clockwise moment of minus 22.5 kilonewton. That is because this is anti-clockwise, so 15 times 1.5, that is minus 22.5. Now, at support A, the division is carried out as in example 3. The only difference is that the moments at support A will be maintained at a magnitude of 22.5 kilonewton meter. That is taking sign convention into consideration. So we go ahead. What do we do? First, we calculate the stiffness factor. For here, we say for the sake of stiffness factor, this place is considered as simply supported. So simply supported here, continuous here. So it's like simply supported and fixed. That will be 3 EI over L. We have this. This one is this span continuous here, fixed here. So it's like fixed 4 EI over L. So we calculate that. We go ahead and calculate the distribution factor. The distribution factor here and here will be 1. So 1 we need to calculate the distribution factor at B, which we calculated as this. So we calculate the fixed end moment as usual, calculate the fixed end moment, and then we do the distribution. The distribution, we first of all put the stiffness or the distribution factor, and then the fixed end moment. We have calculated the fixed end moment here to be minus 40, 40 minus 106.5, then 106.5. At this point, remember, the moment here is 22.5. Why is it 22.5 when we did here is anti-clockwise? Okay, the explanation is that this moment here is anti-clockwise. But the moment we always keep as fixed moment at the resistive moment. So if this is anti-clockwise, the resistive moment has to be clockwise. That's why we have this 20. But then the anti-clockwise is actually at this point. If you remember, in all our moment, the left in any span, the left support is usually negative, the right support is usually positive. So that means this negative 22 is actually should be here, which will be our final result here. So what do we do? This is this point is 22.5. We have minus 40 here. We need to balance this load such that what we will have here will be minus 22.5, because that is actually what is resisting this place. So this place is actually what is resisting this cantilever. So what do we do? This minus this gives us minus 17.50. But for us to balance, we're going to introduce a clockwise moment of the same magnitude. That is a moment of the same magnitude but opposite in direction, which is what? 17.5. So by 17.5, if we now do minus 40 plus 17.5, you see we have minus 22.5, which is what we want. We want the moment here to be due to the cantilever. So once we do that, we don't balance, we don't take over any moment to that support, but we can carry it over once to the other side. So we now come to other joint and balance. Balance here, we have this moment. We carry over this one here. We don't carry over any moment to that because we don't want the moment to change from this what we have had. We carry over this to here because it is fixed. We now have this moment. We balance it, carry over here. We are not carrying over anything here. So once we sum the moment, this is what we have. So at this support, the moment is 22.5. Negative at the right side, positive at the left side. So we map this and we have this. And the next one is to support, calculate the support reaction using the principle of statics. We now calculate the support reaction. VA is this, VB is this, VC. So we now go ahead to draw a bending moment diagram in the usual way. So this is the load, this is a shear force diagram, and this is the bending moment diagram. Notice the way the bending moment diagram here, there is no this other span, cantilever span, there is no load, there is no simple support moment to superimpose. So it's just only the support moment that is here. This one is usual, this one is usual. So that is it for the case where we have a cantilever. In this part, we have been able to look at the case where we have a simple support and the case where we have cantilever at either of the ends. So this is where we end for part 3. In part 4, we are going to look at when we have, how do we use moment distribution when we have a support settlement. That's what we are going to look at in part 4 of this lesson. Thank you for watching to this stage. Please remember to subscribe to this page and like this video. Thank you very much.